Hello, and welcome to the Self-Learning Flow Reactor Project with Group 16, Daniel Kloisner, Dylan Carzello, and myself, Jason Dumont, under the guidance of our faculty advisor, Dr. Matthew Stuber, and our industry sponsor, Boehringer Ingelheim. Before getting into the purpose behind this project, we would like to talk about the sponsor behind it. Boehringer Ingelheim is a research-oriented biopharmaceutical company which strives to develop innovative new healthcare products. This industry giant, currently known as the largest privately owned pharmaceutical company in the world, is currently working on around 100 clinical and preclinical pipeline projects, many of which will require upscaled production, which in turn will require quite a bit of process optimization along the way. Speaking of production, in this case we have multiple scales of production to discuss in terms of our project, which span from the R&D process to even wide-scale manufacturing for the market. First off, we have bench-scale production, which is on the smaller side and usually faces a bottleneck in terms of the speed of which a chemist can work and how much time they can work in a day. Meanwhile, we have full-scale production, which faces its own bottleneck in terms of feed input and waste disposal. Our project mainly deals with bench-scale processes, but in the future can be scaled up to full-scale production. The goal of our project is to automate the process of finding the most optimal way to run a particular reaction by inserting our product into the existing Boehringer Ingelheim lab setup. Optimizing a new process is expensive, both in terms of time and resources. A lot of this time is taken up by humans adjusting variables manually, be it temperature in a heat exchanger or the rate of certain pumps, which in many cases means stopping the process before restarting with the altered variable. This allows for a degree of human error, which can both interfere with the results and in some cases potentially lead to worker injury. By getting a computer to run this optimization on its own, we streamline this process and remove most of, if not all, cases of human error.
Before taking our work into the lab, we had to prove our optimization algorithms worked. We created a digital twin of a plug flow reactor, modeling the first reaction in the production of ibuprofen. In our first approach, we modeled the plug flow reactor using numerical methods, including the method of lines, finite differencing, and Runge-Kutta-4 integration. Unfortunately, this resulted in some numerical instability in our model. We changed our approach by using upwinded differencing, and we used the ODE23S solver in MATLAB for integration. This allowed us to dynamically model the reaction with flow rates, inlet concentrations, and ambient temperature changing with time. We were able to predict the concentrations and temperature at every point in the PFR at any time. We then were able to test optimization algorithms on this simulated system and prove our ideas without wasting time and resources in a lab. We had to decide between two different approaches to optimization. The first approach is a type of optimization algorithm called the direct search method. In direct search, the algorithm uses gradient information to find a local minimum of the objective function in the search space. This is advantageous because a relatively small number of samples may be sufficient to determine the minimum. The second approach uses surrogate modeling. This is a more traditional approach where the entire search space is sampled using factorial design of experiments. Using the experimental data, parameters of an assumed model are estimated using a least squares regression. Once the model parameters are generated, the minimum of that model is found. The advantage of this type of approach is that you find a global optimization. With direct search approach, you cannot be sure that you have found the actual minimum, only a local one. We settled on the surrogate modeling approach. To implement surrogate modeling, we sampled points in the search space with a full factorial design of experiments approach. In this scheme, the extremal values of the design variables are tested, along with regularly spaced intermediate values. Other schemes, such as Latin hypercube or Monte Carlo sampling, may also be used. The resulting values were then regressed to a model with linear and bilinear terms, from which the optimal design parameters were obtained.
Boehringer Ingelheim's lab setup includes pumps, the reactors, a heat exchanger, and the computer controlling these devices. The useful software on the computer is ReactIR, LabVIEW, and MATLAB. The readings we get from ReactIR about the system can be sent to our LabVIEW and MATLAB code, where our optimization and control algorithms can then be applied to their system, keeping it running at optimal conditions. We will be using a feedback control scheme, taking readings at the output of the process to in turn adjust our inputs to reach a particular optimal point towards a goal. Now let's take a look at the economics of our project. Since our project is all code that we can apply to an existing system, our solution is very cheap. The productivity would increase in the lab because the chemists would have more free time since we are automating many experiments with our code. Doing an EHS analysis, we can see that with our cheap optimization, it would be easier to reduce waste and energy usage in BI's lab. Also, workplace injuries would be reduced due to the automation of the lab processes.
This concludes our presentation on the Self-Learning Flow Reactor project. Thank you for your time and have a great day.